It's a shame from the presentation.
Hello, my presentation is about the effects of a merger on star formation rate. I'm a high school student from the McDuffie School. It's in Massachusetts. And first of all, I would like to thank my advisors, Professor Jeyhan Kartaltepe and a PhD student here at RIT, Ekta Shah, for making this all possible. So let's start off with an overview of what a merger is. A merger is an interaction between two galaxies that result in them blending together. And even though this process takes millions of years to happen, astronomers can look at various mergers from different stages of interaction to determine the effects of such an event, as you can see here. Another key word that we really need to understand when we talk about galaxy interaction is gas fraction. So gas fraction is simply the ratio of gas mass to the total mass in a galaxy. And why is this important? It's important because gas is fuel to star formation. It's because stars are just hot balls of gas. So high gas fraction tends to lead to high star formation rate. Another important trend that we need to be aware of is how star formation rate varies with redshift. Redshift is simply a measure of distance. And we just need to know that galaxies from different ranges of redshift have different properties. And one of these properties is their star formation rate. As you can see here, galaxies at redshift 2 tend to have higher star formation rates than galaxies that are nearby us. This also means that galaxies with high star formation rates have high gas fraction. These are two simulated images of a galaxy. The color bar highlights the area with the densest region of gas as yellow. So on the image on the left here is a typical galaxy at around redshift of 0.05. It has a gas fraction of about 10%, and the densest area with gas is in the center where most of the star formation happens. Another things to notice are that the spiral of the galaxies are very structured. This means that the system is very stable and the gas inside the galaxy isn't moving as fast. The image on the right, however, is a typical galaxy at around redshift 2. Has a gas fraction of 60%, which is way higher than the image on the left. And the clump of gas are spread throughout the galaxy planes, which means that the high gas fraction, the gas inside the galaxy are moving very fast and it is very unstable, and the system is very disturbed. So what effect does galaxy interaction have on star formation rate? These are two simulations of emergent interaction between the two different galaxies that I have just discussed about. And here, I'm just going to play it. So the gravitational effect between the two galaxies usually cause the gas to flow inwards and to the center of each galaxy, and tends to lead to an increase in the galaxy star formation rate. And we see that a lot with the galaxy on the left here that has the lower gas fraction. We can see that the gas is very concentrated in the center, and this increases their star formation rate by a lot. However, in the galaxy on the right, we can still see that there are a bunch of clumps of gas throughout the galaxy plane, and we actually don't see the same increase in star formation rate. This simulation shows that a merger between two high gas fraction galaxies result in a lower enhancement in star formation rate than its counterpart that has low gas fraction. However, the results from a simulation alone are not enough to make an indisputable claim, and that's why we need observational evidence. This is the motivation for our project. So we would like to measure the gas fraction of interacting galaxy pairs that are lower than redshift 3, and then compare the star formation rate of these pairs that vary in gas fractions. At the beginning of this project, my advisor, Ekta Shah, had sent me the positions, redshift, and stellar mass of around 2,000 galaxy pairs that she identified from optical observations. However, because light in optical wavelengths is mostly coming from stars and cannot be used to accurately calculate gas fractions, we have to use submillimeter observations. Light in submillimeter wavelengths have mostly been absorbed and re-emitted by dust particles. And thus, by measuring a galaxy's brightness in this wavelength, we can calculate the gas fraction. So where would I get the submillimeter observations? I got it from ALMA. ALMA stands for Antakama Large Millimeter Array. It's a millimeter telescope. However, because I only want images that fall within the wavelength of 0.8 to 1.4, which is ideal to observe dust and gas, and I only want images that contain at least one of our galaxy, I had to use a data mining tool called AstroCrate. So I ended up with around 1,500 astronomical images that contain roughly 1,000 of our galaxy. But considering that almost all of the observations were not targeted at our galaxy, meaning that our galaxy just accidentally happened to fall in an image targeted at something else, we really didn't expect to find this many of them. So this image is one of the 1,500 astronomical images that we downloaded from ALMA, and about 47 of our galaxies fall in this region, marked by the red dots. I'm not sure if you can see. But however, there are faint and bright galaxies in this field. So not all galaxies are bright enough to be used to measure their gas fractions. So I had to figure out a way to separate the bright ones from the faint ones. But for time purpose, I'm not going to go into that. And let's just say that I got 7 bright ones that I can use to calculate the gas fraction. Here are 2 of them. You can see that they're definitely brighter than their backgrounds. So we started with 4,000 galaxies. So 2,000 galaxy pairs is 4,000 galaxies. And around 1,000 of them were observed by ALMA previously, and 96 of them were bright enough to be used for calculation. Now, to make sure that our methodology is consistent with past literature, so past papers, we compared the measured brightness of our galaxy with a published paper that from a while ago. So around 10 of our galaxies were previously measured. So we compare our brightness with those galaxies. Another word for brightness is flux, by the way. And so we compare the flux, and if our flux value are similar, they would be near this line. So we can see that this method of measuring the flux is consistent with past research. Now, how do we go from brightness to gas fraction? So as I've said before, the dust of a galaxy, the dust inside a galaxy absorbs and re-emits light at a higher wavelength. And from this relationship, I can approximate the dust mass using the apparent brightness. But dust isn't the same as gas though. So how do we go from dust to gas? It turns out that there's also a relationship between dust mass and gas mass, and a ratio between them has already been incorporated into this equation. We just have to plug in our variables, which are the apparent brightness or the flux, the redshift, distance, and the observed wavelength. The other values are mostly constants that were approximated in past papers. So after we calculated the gas fraction values, we plotted them as a function of redshift. And as we would expect, most of the galaxies that have gas fraction of lower than of pretty low around here fall within the lower redshifts. And gas fraction values that are higher than 75% mostly fall within the higher redshift ranges. This is a plot that shows star formation rate in the y-axis to stellar mass in the x-axis. And the lines here are what we call the main sequence, which is what a typical galaxy in that redshift range would, the typical star formation rate at a given redshift range. However, we don't have enough data points to make a statistically significant claim that an interacting galaxy pair would have higher star formation rate than a typical galaxy. So the most important part of our project, however, is to compare galaxy pairs that differ in gas fractions. But out of the 2,000 pairs that we had, we only found 6 pairs that we have both galaxies detected. So that's definitely not enough data to make a claim. Here is one of our pair. The left image is the subliminal image of that pair, and the right image is the optical image of that pair. So what I did here is I plotted a contour, which is just levels of brightness in an image onto the subliminal image, and then superimpose it onto the optical image. We can see that there are some structural structural similarities here with this contour and here. However, this suggests that there is some gravitational effect that causes the gas to move down towards the center of the curve. Now, what does all this mean and what are the next steps? Because we only have the star formation rate of about 50 of our galaxies that were detected out of the 96 detections, a next step would be to estimate the star formation rate for the rest of the detected galaxies. Another future work could be to stack the images of galaxy pairs that were observed but not bright enough to be used as measurements for gas fractions. Then we can compare the stacked galaxy pair image with a typical isolated galaxy and then determine if the effect of such an interaction have any influence on the brightness or the gas fraction of the galaxy. However, even after we do all of that, we would still not have enough data to make a strong claim that merger between two high gas fraction galaxies result in an effect that is different from low gas fraction galaxies. This means that we would need the ALMA telescope to observe more of our galaxies. To do that, we would submit a proposal. And because we have looked at every possible observation that contains our galaxies and still do not have sufficient data to make any claim, this will make a very strong case for